This serves as a review of our chapter on exponentials and logs, minus the graphing. The graphing is not part of this review. I'm going to do in each box of these questions. This is different than the previous review that you did, but I'm going to do one of them and leave the other three to you. Okay, so let's take a look at our first selection here, which is compound interest. For each of these compound interest, we would start with this base formula y equals a b to the x, where b is the rate that the investment is growing, and a is our start amount, and y is our end amount. However, for compound interest, we need to account for not only that we should start at 100% of our investment, but we need to add to it our rate of investment, in this case the 5.35%. But it is compounded monthly, which means we are not going to get all 5.35%. We're going to get a twelfth of it each time, so we need to divide that by 12. So I essentially end up getting 1 plus 0.0535 divided by 12 right there. And I would take all of that and put it into B right there, thus resulting in 8,000. Whatever 1 plus 0.053 divide 12 is, I would type all of that in. And then X is our time units. Our time units is actually not going to be years. It's going to be 3 times 12 for 36 because I'm going to compound this 36 times. I'll type all of that into my calculator and get, since it's money, $9,000 with 42 cents. So $9,375.42. In a compounded continuously question, which we see here in these four, continuously, I need to use this formula. A difference in this formula is not only the E, but the fact that I don't need to account for that 100% that the rate normally starts at. It's built in because of the E. So I have 5,800 E. Now this is all an exponent of the E, 0.075, change that percentage, times 6. And when I type all of that in, I get a value of $9,096.21. All right, population models of any kind are going to start with that initial exponential model that I showed at the beginning. I'm going to do number 10. So we have a population of a colony decreases, or we could say they're dying, or any synonym that would mean that the population is going down, exponentially at 5% annually. So I start with this. A is my initial amount. Now our B, our rate, well, our rate should start at 100%. We're decreasing at 5%, so we subtract the 5%. And that gives 95%. So going in here is 0.95. Since it's an annual rate and we're going in 5 years, we'll put a 5 right there. And now we type it all in. And we get 3,000 $95. Well, it's not money, so $3,095, and done. Okay. This is these are examples where you have some sort of model that you need to develop based upon the numbers that you're given. So let's take a look at, say, number 14. The population starts in 2010 at 5,600 and becomes 6,200. What will be in 2024? So we again start with this formula. And basically, for exponential models, it is this formula unless it's continuous. You see the keyword continuously. All right, so we know that we start with 5,600. We know we're going to end up with 6,200. We don't know the rate of population growth or decay, but we do know that it takes 4 years to get to this new population. So I'm going to solve this to get my rate of growth, or in some cases, decay. I want to keep lots of decimal places because they do make a difference. And now in order to solve this, I need to take the fourth root. And I get 1.02577. Now that's keeping actually all the decimal places up there. If your calculator doesn't do the fourth root, you can do caret, parentheses 1/4, like that. That's basically switching it to an exponential, so you need to remember that the fourth root of x is the same thing as saying to the 1/4 power. Okay, I'm not done. This gives me the rate in order to solve the problem, so I want to know the population. Again, I'm starting at 5,600. I want to know the population in year 2024. So I pop in my rate, and I pop in my time. From 2010 to 2024 is 14 years. Now I type all of that into the calculator. And get a population of 7,997. Rounding up. All right, half-life problems. Half-life, the only difference is that we know that, well, there's two differences. First of all, our time is measured in number of half-lives, and our rate is always 0.5, or half. I'll do number 17. The half-life of an element is 12 days. How long until 300 grams of that element turns to only 100 grams? So we start with something like this. And we need to know that this x is number of half-lives, which would be time over h. You could put this time over h in here. I think it makes it unnecessarily complicated for what needs to happen to have it there at the beginning, so we can just deal with it at the end, which is what I would like to do. But you could do whatever the heck you want. Just do it right. So at the end, we want 100 grams. We start off with 300 grams. Our rate is 0.5. And we want to know how long this takes. Now, 0.5, I can't multiply these because this is in exponents. Exponents first, order of operations. But I could divide by the 300, so I will. And then, the whole point of this chapter was to solve when our variable is the exponent, and we know that we should log both sides in order to do that. Now on my calculator, I'm actually keeping more decimal places there, so don't be surprised if you typed in exactly 0.333, that you'll get a slightly different answer than me. When we log both sides, this exponent comes out to the front. So I'll get log 0.333 equals log 0.5 with an x out here. Now I can divide by log 0.5. And that gives me, we'll find out, 1.585. Now, that's the number of half-lives. So if I come back up here, I know that my time is over the half-life of 12, so I need to multiply this by 12. And that gives me 19 days as the time unit. So if we were to check this and we were to put a 19 over 12 right here, if we were to replace this with 19 over 12, it should come out to approximately 100, which I'm checking that right now. And yeah, 100.1, so pretty close. Evaluating logs should be one of the simpler things from the chapter. Most of your calculators have built in the log base. So if it does, you can go ahead and do that. But if it doesn't, it's good to know the change of base formula. And to tell you, the change of base formula is this. The argument goes up, the base goes down. So that's what I'm doing right here. And it actually turns out to be faster to just do the change of base formula than to go into the menus of the calculator to find the log base. And there we've evaluated the log. Now since we're on this screen, I'm going to go ahead and remind you what log even means. So if I have some base to some exponent equals some answer, this is exponential form. In log form, that would be log base b of a gives me my exponent. So this is something that you definitely need to know. It's the basis of the entire chapter. And if log is not given, it's 10, or the base of the log not given is 10. And if it's ln, the base is e. Okay? Again, getting to the heart of the chapter, being able to solve these exponentials, we need to log both sides. And when we do, the exponent comes out. So many of you in your work have been skipping a step, which is okay, because you basically always, when you have these, are always going to have this situation come up. Now we distribute the log 9 and the log 6. And we're being careful that this x is not inside the argument here, because that would mean something different. Now we're going to collect our x's to one side. In this case, I'm going to collect it over here. So I'm going to add it, and then I'm going to add this over here, just to keep my x's positive. So I'll have 4 log 6 x. I'm going to add this one to the other side. I'm not distributing it. Usually I use the arrows to mean distribute. That's not what I'm doing. I'm adding this. I'm going to add this one. So I'm going to add it to over here. And now I see an x is common, so I can factor it out. And now I can divide by that whole thing. So I'm going to save myself some space here. Cheat a little bit. Since I am running out of it. This is a poorly drawn 6. And a poorly drawn 9. Alright, here we go. This is the exact answer. And then if I type that into my calculator, I can get an approximate. And I get x is approximately 4.576. So all of these, except for maybe 28, so I'll just give you a hint. When you log 28, you don't have x's over here. So it actually makes it simpler because you don't have an x in the exponent over there. All right. When we have e in the mix, we need to use ln because ln is base e. It makes it much simpler. So we'll add the 4. We need to get this part alone right here. Always. So I have a number in front, so I'm going to have to divide by that. I'm not going to do that first. I'm going to add the 4 first. It gives me 27. Now I divide by the 4. And now I can ln both sides. When I do, the exponent comes out. You could type this in your calculator, get a number. I'm just not bothering. ln e is 1. So we need to remember, like, whenever I log and the base and the argument is the same, I get 1. Thus, ln e is 1. So this is just 1, and 1 times anything is that thing. So I have 20 minus 6x equals ln 27 divide 4. Subtract the 20, divide by 6. So I'll put the answer up here. I get 6, or x equals, again, subtract the 20, divide by 6. ln 27 over 4 minus 20 divided by 6. And I get x is approximately negative 3.015. And these each work similarly. Okay, now we need to start using the properties of logs in order to solve. So really quick, I'll put them right here. So if I have log of A plus log of B, that gives me log of A times B. And if I have log of A minus log of B, I have the quotient rule, A over B. I can bring it in, so I can bring these into a single log. And then if I had some number in front being multiplied, this can come in as an exponent. Okay, I am going to do 33 and 36. We see a power rule, or a product rule here, which means I can multiply those. Now, this is base e. So e to the third, this would be our exponent, equals 12x. And thus e to the third divided by 12 And then I can put that in the calculator to get an estimate if I wanted, which I do. So x is approximately 1.674. Alright, I will do number 36. This 2 can come in as an exponent, thus giving me log of 9. This is again a product rule, so bring it together and I get log 36 equals 2, 36x. Now, the base isn't written, so it's 10. So 10 squared equals 36x. So 100 equals 36x. So divide by 36. You can get approximately 2.778. If you just wrote that as a fraction when you did 100 divided 36, you get 25 over 9 exactly. Okay, more log equations. I will do these two. Actually, maybe just one of them. I'll do this one. Because it's ln. It's a minus in between, so that's a quotient rule. So we'll have ln when I bring it in, 5 over 4 minus 2x equals 4. It's base e, so e to the fourth will equal 5 over 4x minus 2, or 4 minus 2x. I'll clear, or cross multiply, and I get e to the fourth equals 4 minus 2x equals 5. Now at this point you have lots of options to solve this. I will decide to divide by e to the fourth. And then I'll subtract the 4. So I'll continue up here. Then I'll divide by negative 2. And this is our exact answer. I divided each of those by negative 2. So let's see what we get. Typing it in. And we get x is approximately 1.954. Alright, getting down to the end here. Expanding. I will do number 43. So, expanding means as a list of addition and subtraction of logs. So, basically using those properties of logs. So I'm just going to work on this denominator a little bit. I'll have 6 to the 4th in the denominator, a z to the 8th. So everything in the numerator at the top is going to be a product rule, and we're dividing by whatever's in the denominator, so that would be a quotient rule. So 6 log x plus 3 log y minus, now this is what's in the denominator, so 4 log base 6, this is base 6 for all of these, of 6 minus 8 log base 6 of z. Now this right here will follow this rule. If you have log base x of x, that equals 1. So log base 6 of 6 is 1. And negative 4 times 1 is negative 4. So, and you might want to put the minus 4 last, but this would be our expansion. Alright, and pretty sure this is the last thing. And let's do number 47. 48. I'll do 48. Leave these for you. 48 is much more difficult. So these all are going to come in as exponents, but I made this tricky exponents. So condensed into a single log, I should have only one logarithm here. So everything that's a plus is going to be in the numerator. And everything that's a minus is in the denominator. Except it's not a y, it's a z. Now, you could write this in radical form. So I see these have the same exponent, so I could write them in the same radical. So I could say square root x cubed y, because these are both the square root. And then down here, cube root z to the fourth. And then hopefully you see you could divide up that z into z cubed in z from the previous chapter and do the cube root of z cubed. And we won't bother rationalizing. We'll just say that's it. Okay, that is the second time going through your review. So try all the other questions and I'll post the answers shortly.